In this video, we're going to look at two of the exercises from the growth models exercises. First one is number 6. Diseases tend to spread according to the exponential growth model. In the early days of AIDS, the growth factor, i.e., which means also known as, also called, that is, the common ratio or growth multiplier, and growth multiplier is the terminology that was used in our book, was around 2.1. In 1983, about 2,000 people in the U.S. died of AIDS. If the trend had continued unchecked, how many people would have died from AIDS in 2004? So first of all, we're looking at an exponential growth model, and here is our formula for exponential growth. P sub n equals the quantity 1 plus r to the nth power times p sub 0. I have a little note over here that the 1 plus r is called the growth multiplier. And we're already given that full quantity. 1 plus r is 2.1 because up here in the question over here it said the growth multiplier was around 2.1. So we're going to plug in here for the 1 plus r, we'll plug in 2.1. To find out our n, we're going to subtract. The year we want to know for is 2004. The year we're starting with is our initial year is 1983. So we'll subtract 2004 minus 1983 to find out that we're 21 years later. So 21 is our n here. And so we'll just plug in P for the year 21. Is 2.1, our growth multiplier, to the 21st power, times 2,000, the initial number given in the problem. And when we do that out, we find out that it would have been 11,685,174,040 people. Whoops. Not what I wanted to do there. The second problem we're going to look at is a logistic growth problem. So this is number 9. Assuming there is a certain population of fish in a pond whose growth is described by the logistic equation. It is estimated that the carrying capacity for the pond is 1,700 fish. Absent constraints, the population would grow by 130% per year. The starting population is given by P sub 0 equals 100. Then after one breeding season, the population of the pond is given by, we're asked to find that, which will be P sub 1 after one breeding season. So the general equation, the general logistic equation is this. Let's break that down. P sub n is the nth year. So if we're looking for the first year, after one breeding season, we're looking at P sub 1. If we wanted after 5 seasons, it would be P sub 5. P sub n minus 1 is the year before that. So in our case, we want P sub 1. P sub n minus 1 is P sub 0, which is nice because that's a piece of information we were given. R is the growth rate. In other words, the rate the population would grow by. And we want to use that as a decimal. And then K, capital K, is the carrying capacity of the pond. So when we plug those numbers in, we're looking for P sub 1. So we'll start with our P sub 0, which we are given right here. 130% is our growth rate, and again, we want to use that as a decimal. And when we plug in our P sub 0 and our K here, and I didn't actually write that out, and I probably should have, it would have been 100 over 1,700. Okay? And when you do that division and then subtract it from 1, you get this decimal. Times again our P sub n minus 1, which is P sub 0, so our 100. When you do all that out, you get the population after one breeding season would be this. After 2 breeding seasons, what we do is we use that population from after 1 breeding season to do the 2nd breeding season. So it's the same exact process, except now what I want is P sub 2. And so I'm going to use P sub 1 in all these places to help me with that. So I'm going to plug in P sub 1 here, here, and here. And when I do all this arithmetic on my handy dandy calculator, I will end up with this population for P sub 2.